Barral from University of the Paris North. He will speak about dimensions of a random statistical self-affine sponges. Okay, Julien, please.
Thank you very much. Thank you to the organizer for their very kind invitation. So I'm going to present you the most recent result I obtained with one of my former PhD students, Guillaume Benet, about some statistically self-affine sponges. And this work is strongly based and inspired by previous works I achieved together with Fong De Jun. Okay, so let me, yes, excuse me. So at the very beginning, I didn't understand that I had only 30 minutes. So maybe my abstract was a little bit ambitious. So I will restrict my talk to result regarding self-affine Gazura-Slale sponges, as you will see. But for the moment, I would like to introduce the notations. They are quite standard. So I consider a finite IFS made of strictly contractive affine maps, which are supposed to be invertible. So these maps are indexed by a finite set I. And as I will assume that they have no common fixed point. Okay, so that the attractor of the IFS, that is the unique non-empty compact set such that this functional equation holds is non-trivial. This set can be seen as the image of the symbolic space based on the alphabet of the indexes I via the coding map, which definition is repeated here. And for any probability vector pi, p in the with entries indexed by I, okay, there is a unique self-affine measure defined as supported on K, okay, defined as it was defined in the previous talk, or if you prefer, defined as the image via the coding map of the Bernoulli product measure generated by this probability vector. Okay. And basic questions that people of our community are looking at quite intensively in the last decade and even before is how to compute via formulas the Hausdorff dimension of the attractor K, or the Hausdorff dimension of such a self-affine measure. And is there any variational principle relating the Hausdorff dimension of the attractor and to the Hausdorff dimension of these self-affine measures? Or more generally, is it possible to approximate the Hausdorff dimension of the attractor by the Hausdorff dimension of image of ergodic measures through the coding map? And we know that the answer in general, the answer is subtler than that. Okay, but these are the, I think, immediate questions that come into mind. Okay, so in this talk, I will restrict myself to a typical situation where the other dimension of the attractor is strictly smaller than the box dimension. That is, there are structurally a lot of overlaps in the definition of these attractors. And so I will consider carpets and sponges. And as I already said, I will restrict myself to Gazuras, Lale, carpets, and sponges. And we'll start by considering the Sierpinski case to recall the results that are known about statistically self-affine such sets. Okay, and I will focus on possible variational principles to express the dimensions, to relate the dimensions of such random sets to the dimensions of some random measures, natural random measures supported on these sets. Okay, so I quickly remind you what is a random statistically self-affine Sierpinski carpet. So we fix two integers, m1 bigger than m2, larger than or equal to 2. And to refer to the notation introduced before, I start with a deterministic attractor, which is just the unit square, and it is the attractor of associated to the natural family of constructions that you introduce when you want to obtain the sub m1 m2 adic rectangles of the first generation inside the unit square. Okay, and to get a random attractor, just consider random subset of the set of indices of these maps. Okay, so it is just a random subset of the product of these two alphabets, and so it is this random subset is picked according to a given law fixed once for all, and you assume that the expected number of elements of this random set is strictly larger than 1. So that means that at the first generation, you just keep a certain random subset of the subsets of rectangles of the first generation. Okay, and then you repeat the selection, but inside each of the rectangles that have been kept. Okay, and you do that in such a way that the selections are done independently of each other in different subrectangles, and you continue this indefinitely. What you get is a geometric realization of a Galton-Watson tree, which is supercritical due to the assumption that you have made about the expected cardinality. Okay, so with positive probabilities, there is in the limit a random counter set which is not empty. Okay, and you are interested in the dimension of this set. So this problem has been studied in the deterministic case, as it is well known. This problem has been studied by Bedford and Macmillan independently in the 80s, and then by Gazuras and Lallet for the random case I have just described. And the solution is strongly related to some pressure function, which is defined as follows. So if you consider the selection at the first generation, what is important? So in any case, in the case that the selection is purely deterministic, the case considered by Bedford and Macmillan, or in the random case, what is important is the number of, for each row that you meet in the first generation, so for each row of rectangles, what is important is the number of rectangles that have been kept in the selection. Okay, so you have M2 such a row, okay, or line, and you count the number of rectangles that have been kept. Okay, call it NL if the line is indexed by L. Okay, so that's the cardinality of the total number of rectangles is just the summation over all the lines of these numbers. Okay, and the pressure function is given by this formula. In the deterministic case, this function is always non-decreasing, but in the random case, and this is what makes the random situation quite colorful, you have the possibility that the expected number of rectangles that you kept in a certain row is strictly smaller than 1. And this makes the situation quite more difficult, okay? So I repeat a result by, I remind the result by Bedford and Macmillan, and also Gazuras and Lallet. Consider this pressure function, and also consider the points theta 0 at which this mapping reaches its minimum whenever it is strictly convex. And take theta 0 equal to 1 when the function is not strictly convex. That means it is constant, and all these expectations are equal to 1. Okay, then you have a formula for the dimension of the attractor whenever it is not empty, and which is formulating like that. But what I will be most interested in this talk is that it can be recovered in the deterministic case as the maximum of the dimensions of the Bernoulli measures carried by the attractor. And in the random situation, it will be the maximum of the dimensions of Mandelbrot measures, which are supported on the attractor. I will, so our contribution with Wang Dejun was to extend the variational principle that holds with Bernoulli measure in the deterministic case to the situation, to the random situation. And it should be pointed that so this variational approach was used by Macmillan in the deterministic case with a kind of miracle that there is a unique measure of maximal dimension, and this dimension can also be used not only to find a lower bound for the dimension, but also a sharp upper bound. Such a nice phenomenon is not true in the random case. You have a nice measure, Mandelbrot measure, which gives you the maximum, but you cannot exploit it in general to find upper bound, and then you have to use, as did Bedford and Getzoras-Laley, you have to use some nice coverings, or use the coverings provided by Bedford and then Getzoras-Laley for the random case. Okay, there is also a formula for the box dimension. Well, so, but I have to remember what is a Mandelbrot measure in order to make my purpose more clear, because of course these objects appear in this variational principle. So I would like to be as brief as possible about this point. So you want to construct simultaneously with your attractor, you want to construct some random measures. And Mandelbrot measures, they are the measure counterpart of, I have to say this in English. Okay. Mandelbrot measures are to these random attractors what Bernoulli measures are to the deterministic version of the attractors. Okay. So what you are doing, so in gray, I have kept a certain squares, rectangles at the first generation, and I want to put a weight, okay, on these rectangles, and these weights can be positive only if I am working on these selected rectangles, so that I will choose weights which are 0 when I didn't keep the rectangles, and they can be positive if I kept a rectangle. Okay, and this is a randomization of the action consisting of distributing a deterministic random vector. That is, we will have as a property that the summation of the weights that we distribute is equal to 1 in expectation. Okay, and once we are given such a random vector, then we can construct exactly like when we distribute a mass to construct a Bernoulli measure. Okay. At first generation, we distribute uniformly the weights we had chosen. Then, if we go to one subrectangle, we will distribute to its sun when they have been selected a mass which is just equal to the mass of the rectangle of the first generation times the mass, okay, corresponding to the index of its sun. And the difference with respect to the deterministic case is that we have to take random weights, and the random weights are taken according to the same law that had been used to get the first generation. And then you iterate. That is, once you know the mass at generation n-1, when you consider a rectangle indexed by a word of length n, I1 until in, okay, once you know the mass of the rectangle corresponding to the word truncated at n-1, you get the mass of the rectangle at generation n just by multiplying the mass of its father at generation n-1 by a weight which corresponds to the copy of the original weights associated to the rectangle, to the father. Okay, so this gives you a sequence of random measures. It converges almost surely weakly to a limiting measure, and this measure is called the Mandelbrot measure, and it is supported by the attractor, by construction. An important point to have in mind is that such a measure is not equal to 0 with positive probability if and only if the quantity which plays formally a replacement for the entropy of a probability vector is positive. Okay. So what we did with Feng de Jun is that indeed we revisited Gazuras and Lalle's result by making a systematic study of the Hausdorff dimension of Mandelbrot measures, and we exhibited a phenomenon which in some sense make it possible to understand better the formula provided by Gazuras and Lalle. We were able to estimate the LQ spectrum of such a measure according to some moment assumption, and prove that the LQ spectrum is differentiable at 1. And what we found is that, in fact, the dimension of the measure is, so there is a Le Drapé-Young formula for this dimension, and it is a weighted sum of the entropy dimension of the measure, which is not surprising, plus something which is the entropy dimension of according to some weight associated to the Lyapunov exponent, a term which is the entropy dimension of the projection of the measure, but this entropy dimension results from a competition between the dimension, the entropy dimension of the measure, and the entropy dimension of the expectation of the projection of this measure onto the vertical axis. Okay, so there is such a phenomenon which, in some sense, explains the complexity of the formula obtained in the random case with respect to the deterministic case. Okay, so I have to go on. So it's possible to extend Gazuras-Lalle results in higher dimension and also Macmillan-Bedford. In the deterministic case, it was done by Kenyon and Perez, with still the same miracle that there is a unique Bernoulli measure supported on the deterministic attractor, and this measure can be used to get the upper bound for the dimension. And this is also related to, I would say, a famous combinatoric lemma established by Kenyon and Perez at this occasion. Again, there is no such a miracle in the random case. It is possible to extend the Le Drapé-Young formula I have just shown for higher dimensional Mandelbrot measures, but for the upper bound for the dimension, we had to, in some sense, to generalize the approach of Gazuras and Lalle and consider infinitely many ways of providing a nice covering, and then to get infinitely many upper bounds. Every bound given by some weighted topological pressure of associated to some potential, and then optimize this bound. So this was quite surprising, and I would say that it was not so easy to understand why this phenomena came into play. This phenomenon came into play until the recent work I did with Guillaume Brinet, which make it possible to recover this result and understand it much better, I would say. So now I enter into the main topic of the talk. That is, I would like to go from these Sierpinski carpets and sponges to the Gazzura-Slaley ones. So the difference here is that so we still consider IFS made of linear maps whose linear parts are diagonal, and we still keep the fact that the diagonal coefficients are all ranked in the same order, but the diagonal map are not supposed to be equal anymore. Okay, and so geometrically, the kind of assumption we make is as follow. Okay, so if we consider the maps of the system, that's the basic assumption that you have to satisfy to define such attractor is that when you take two different indices in the index set, then excuse me, I have to mention that you can always assume that the unit cube is fixed is stable by the maps of the system. Okay, and you assume that the intersection of two images of the unit square, unit cube, excuse me. Okay, is empty whenever you consider two different indices. Okay, not the intersection, the intersection of the interiors of these sets. Excuse me. Okay. And then when you project on subspaces according to these projections, okay, so from RD to space, when you only retain the D minus R plus 1 coordinates, okay, what you require is that when you take the image of two such interiors of image of the unit squared, either they coincide or they are empty. Okay. In some sense, it's a kind of you can see that here I have taken an example in dimension 2, so it's a Gazzura-Slaley carpet. So indeed, the two different images have disjoint interiors, and when you project on the x2 axis, okay, either the projection coincide or they are disjoint. Okay. They have disjoint in interiors, I mean. Okay. Well, so what is known about these objects in the deterministic case? Gazzura and Laley, okay, they prove the variational the expected variational principle that the other dimension of the attractor is the maximum of the other dimension of the self-affine measure it supports. But there is no uniqueness, contrary to what happens in general, there is no uniqueness, contrary to what happens in the Sierpinski carpet case. Okay. And the impressive results that was a motivation to study the random version of these objects is a result by Das and Simmons, which claims that in dimension larger than or equal to 3, in fact, you cannot expect in general to approximate the other dimension of a Gazzura-Slaley sponge by the dimensions of image on the attractor of ergodic measures. Okay. In fact, Das and Simmons provided an example in which they consider an inhomogeneous Bernoulli measure, okay, that is Bernoulli measures generated by a sequence of probability vectors which are not equal, okay, and they were able to prove that the dimension of such a there exists such a measure whose dimension is strictly larger than the dimension of image of ergodic measures, the supremum of the dimensions of image of ergodic measures, okay, and their inhomogeneous Bernoulli measure has the specificity that it is a restriction to the integers, so the functions which to n as to the generation n associates the probability vector of generation n in this sequence. Okay, it has a specificity to be the restriction to the integers of an exponentially periodic continuous function taking value in the space of probability vectors. They provided a conjecture, they proposed a formula rather than a conjecture, according to which the dimension of the attractor should be given by the supplement of the dimension of such inhomogeneous Bernoulli measures constructed on the attractor. Unfortunately, there is a gap in their proof. And so this led Guillaume Brunet and I to propose another variational principle. It is still based on the dimensions of inhomogeneous Bernoulli measures, but we make the following assumption. That is, we consider any increasing sequence of integers such that the piece term of this sequence is negligible with respect to the sum of the p minus 1 previous terms of the sequence. Okay, so your sequence of integers goes to infinity, but not too fast, not exponentially, like sub-exponentially in some sense. And then you assume that the Bernoulli, you consider inhomogeneous Bernoulli measures so that the weights, the probability vector that you consider are constant over such the intervals of the form LP minus capital LP minus 1 plus 1 LP, okay, that where LP is indeed the partial sum from 1 to p of the sequence small LP, okay? And then the variational principle holds. So I have few time left. So this principle can be extended to the random case. So in the random case, what we do is what we did for carpets, for Sierpinski carpets and sponges. We use a percolation process to construct a random subset of the attractor according to exactly the same process of selection. And we are going to consider not just Bernoulli measures, but inhomogeneous Bernoulli measures, okay? And we can even, in fact, we can even limit ourselves to random such inhomogeneous Mandelbrot measures in which the inhomogeneity will come from the fact that we don't choose copies of the same random weights at each generation. So the random weights depend on the generation, and they are associated to a probability vector which is deterministic and made random by multiplicating by such by this weight, which is related to whether or not the corresponding rectangle is kept in the construction. Okay, and then you get sequences of measures by distributing products of weights which have not the same law, but okay, but according to the same rule as in the homogeneous case, and you get in the limit a random measure. You have ways to at least sufficient conditions under which you know that the limiting measure is not degenerate. It is positive with positive probability. Okay, it is a natural extension of Kn condition. And then you can get the following result. In fact, so if you take such a sequence of integers which goes to infinity sub-exponentially, and if you will say that a Mandelbrot measure is of type L if when you construct it the deterministic part of the random weight is is of type L in the sense defined in the previous theorem. Okay. Then, with probability 1, conditionally on the fact that the random attractor is not empty, you have the fact that the other dimension of the attractor is given by the supremum of the other dimension of those inhomogeneous Mandelbrot measures of type L supported on the attractor. The techniques that we developed to prove this give you also that the packing dimension is equal. You have the same principle for packing dimension. And if you go back, if you suppose that the dimension is 2, or if you suppose that the diagonal matrices are identical, you can in fact use Mandelbrot measures to get the Hausdorff dimension of the attractor. You can also prove that the box dimension exists, and that there is also a formula for this. So if I have, may I have 2 minutes?
Yes, sure.
Okay, thank you. Okay. What I want to express is that I have want to deliver two messages. The first message is for the lower bound for the other dimension. So we have provide a lower bound. In fact, we have to, and this is related also to the upper one. The first step is to be able to compute the Hausdorff dimension of these inhomogeneous measures. Okay. So the point is that if we want to do this, okay, remember that for Mandelbrot measures on Sierpinski sponges or carpets, we can in fact estimate the LQ spectrum and prove that it is differentiable at 1 and provide a nice Le Rapé-Young formula. So now the situation is a bit different. What we have to do, each time we select inhomogeneous Mandelbrot measure. So I repeat that it's the associated random weights are governed by a sequence of probability vectors which are purely deterministic and which are perturbed to take into account that there is a selection. In fact, for each integer n, we can define a sequence of d integers which are very well adapted to the behavior of the Lyapunov exponents of the iteration when you look at points picked mu almost everywhere. Okay, you can produce such a sequence of numbers, and this sequence of number provides you with a nice collection of rectangles which covers your set. You have for each integer n a nice collection of rectangles, and you can build on this collection of rectangles. You can build nice partition functions. Okay, and the expectation of these partition functions can be estimated sharply. And the important thing is that this is what is explained in the following theorem. The important thing is that when you consider when you pick a point in the attractor according to the measure under study, the elements, the nested family of elements of these coverings which contain these points, they look like balls. This is the important thing. And this and in fact you can derive what is the local dimension, the lower local dimension of the measure, and also the upper local dimension of the measure, almost surely with respect to itself. And what you discover is that you have, so while in the deterministic case, you would have, as expected, a sum, in some sense, a sum of contribution by entropies of projections over successive subspaces. Here you have, as like what we observed for Mandelbrot measures, you have a competition of formulae, and you have a competition between GD of n minus G1 of n formulas, in which you get terms which are the entropies of these random weights and also terms which are indeed entropies of projections of these probability vectors, which are the deterministic components of the weights. The formula is even more complicated for the upper local dimension. And but anyway, you get such an expression, and the important thing is that such an expression plays a fundamental role in finding the sharp upper bound. So to resume, to find the sharp upper bound, this is you can reinvest what you learned about the dimension of these inhomogeneous Mandelbrot measures, or even inhomogeneous Bernoulli measures in the deterministic case. And this is where the assumption about the sequence LP comes into play. So I will not detail, but just say that in the works by Bedford and Gazura-Slaley, to find nice coverings, they exploit, they inspect the behavior of the frequency of digits of any point in the attractor. And here we replace this frequency of digits, they compute frequency of digits along the whole sequence of digits, okay, as n tends to infinity. So what we do is different. We consider local frequencies of digits. Okay, so what we place the formal replacement here is that, in fact, we pick such a window, okay, and say it is a local window, and we compute the digit frequencies according to each such window. And this is what has to be exploited to relate the other dimension of the attractor to the other dimensions of the family of inhomogeneous Mandelbrot measures of type L. Okay, this holds whatever be the choice of L. So maybe it's possible to reduce this the family of inhomogeneous measure on which we base the variational principle. This is completely open. Thank you very much.